Hi, my name is Jeff Allred. I'm the lead engineer for Lord MicroStrain's new Torque-Link LXRS product, and I'm here to discuss the specifications and the usage cases for it. First, the Torque-Link is a wireless torque monitoring node. Some highlights: it's a hardened collar available for 2 to 6 inches, approximately 50 to 150 millimeter shaft diameter. All the diameters require a 3.5 inch axial length. We are capable of making diameters smaller than 2 inches and greater than 6 inches, but it requires some custom work, so we need to be contacted for a custom quote in those cases. The reason we call it a hardened collar is some of our main competition uses a similar rotating torque measurement system, but they use a strap, kind of like a Velcro or a Kevlar strap that wraps around the shaft and holds on a product similar to our standard S.r.l, whereas this is a collar that contains potted electronics, completely encapsulated, and then bolts around the shaft to clamp onto it. It's got a much higher holding power than a strap would. It's much more rigid and hardened, better environmental resistance, etc. The strain signal from the board is a 16-bit analog to digital conversion. It transmits data using a 2.4 gigahertz radio, our standard wireless LXRS protocol. Transmits raw torsional strain data, or it can transmit torque data if there is a calibration performed. It can be viewed or analyzed in Sensor Cloud or Node Commander. CSV files from Node Commander can be shared through Sensor Cloud or over email, other transmission methods. This is compatible with all other Lord MicroStrain wireless nodes, so if a customer wants to measure vibration and torque, they could use a G-Link in conjunction with the Torque-Link, for instance, or if they need to measure temperature, they could use a TC-Link with the Torque-Link. And the Torque-Link communicates to all the base stations, WSDA 101, WSDA 104, WSDA 1500, just like all our standard wireless products. The Torque-Link does require strain gauges to be installed on the shaft. We believe that most customers will have this capability in-house. If they do not have this capability, we could potentially install strain gauges for a customer, but that's going to be a custom quote based on the job, volume, complexity of the installation, things of that nature. So the structure of the Torque-Link, it's 2 printed ABS collar halves. The electronics and battery are contained on one side of the collar. The other side is a blank. We do have the capability to do 2 electronic sides if a customer is interested in measuring, say, axial thrust in addition to torque. On the battery side, it's the battery compartment is sealed by a lid that uses 6 Torx head bolts, and the collar itself is bolted together if it's under 2.5 inches with 4 socket head cap screws. If it is greater than 2.5 inches, it takes 6 socket head cap screws. You can see inside the collar there are 2 gauge pockets, one on each side. That's for going over the strain gauge installation. The customer would lay up strain gauges and then apply an epoxy or a poly coat over it, such as M-Coat from Vichy. Wire to another terminal strip, and then wire from a connector that we provide them from the terminal strip to the board. The wires can run through the gauge wiring channel, and it should provide enough clearance to run standard kind of magnet wire or 28-30 gauge coated wire if need be. The inside of the collar also has a small strip on the opposite side from the gauge pocket that'll have VHB tape. We'll install the VHB tape in that strip from the factory, and the customer will be able to remove the covering from the VHB tape prior to installation on the shaft, and they can install it on the shaft and press down. It'll give a better lock, so the collar will be much less likely to slip. We tested it to a 200-pound slip rating using the VHB tape. As I said earlier, the Torque-Link uses strain gauges to measure torsional strain, which can then be converted to torque. At Lord MicroStrain, we recommend a full bridge configuration. You can measure torque with a half bridge, but using a full bridge provides the highest torque accuracy because it doubles the measured torsional strain and cancels shaft bending, radial load, and axial load. Torque can be calculated 2 different ways with this device. First, it can be calculated via dead hang calibration, where a customer has a torque arm with a known length, and then they can hang a known weight on the torque arm to provide a known torque input, correlate that to strain. In those cases, the customer probably would want to have multiple weight increments, for instance 10, 50, and 100 pounds, depending on the length of the torque arm, to get a few different points to be able to create a linear calibration to convert the strain to torque. Then they'll be able to input that into Node Commander, assuming they use a linear calibration y equals mx plus b, and get torque directly from Node Commander. Additionally, the customer could do a theoretical torque conversion, where as long as they perform a strain gauge shunt calibration via Node Commander, they can input the output strain into the equation shown here on the chart, which requires knowledge of shaft diameters and shaft material properties, such as the modulus of elasticity and the Poisson ratio. So the user manual provides very clear instructions for installation of strain gauges to measure torque. So we provide a very clear both strain gauge installation diagram and strain gauge wiring diagram inside the user manual. This is just a snippet of it. Additionally, after installing the Torque-Link, there should be a gap of about 60 thousandths between the flats on each side, and that's across any of the diameters that we're going to sell. And the screws should be torqued to 5 inch-pounds. So all the full installation instructions are contained in the user manual. We recommend to customers that they use Math Engine and Sensor Cloud for the analysis and transmission of data from the Torque-Link. Additionally, if there's a customer that's able to do a lot of analysis on their own, they can import data from Node Commander into Sensor Cloud and then write their own algorithms to analyze the data or do some kind of custom plot if there's this particular phenomenon they're looking to measure. So this plot shows the maximum shaft speed by shaft diameter. This is included on the website in the datasheet. There are higher G applications possible, but it requires changing the crystal on the board to a high G crystal. So that need to contact engineering for the custom applications. We have had applications in the aerospace industry that have spun in excess of 8,000 RPM on I believe a 2.5 inch shaft. So we can certainly go much faster than this, but it does require a little extra work and will require some custom engineering fees. This next chart is for the power draw and battery life. So you can see the two lines. The first is sync sampling at 16 dB, and the second is sync sampling at 0 dB, so our high power setting, our low power setting. You can see it's a pretty small difference between the two, and then below 16 Hertz there's really no difference between them. But using the 16 dBm and the included battery pack, we're looking at a conservative life estimates of 33 hours for 512 Hz synchronous sampling, 75 hours for 128 Hz synchronous sampling, 327 hours for 16 Hz synchronous sampling, and well in excess of 5,000 hours for 1 Hz. 20 Hz, for instance, would be a 1200 RPM shaft. 1800 RPM would be a 30 Hz shaft. Some suggested applications for the Torque-Link include reliable replacement for slip rings and test and measurement application. Lord has had a couple of customers that have used this for aerospace flight tests where they've been previously using slip rings and then had slip ring failures, and in order to get back on test quickly went with a wireless approach. So Lord provided custom Torque-Links in very quick turnaround times on the order of a couple of weeks for the customer to continue their flight tests and get their UAVs approved. Additionally, we believe that off-highway vehicles are going to be a very big market for the Torque-Link. Those often use slip rings on their proving grounds and development tests, and when the slip ring fails, it requires removal of the entire drive shaft or axle, wherever the torque's being measured from, to remove the slip ring. Slip rings often last on the order of 1 to 200 hours. They fail fairly rapidly, especially compared to what the Torque-Link will do. And if a Torque-Link does fail or it needs some maintenance or there's a problem with the strain gauges, it's a very easy removal and reinstallation process. As opposed to a few hours for removing an entire drive shaft and replacing a slip ring, it's about 2 minutes to unbolt the Torque-Link and then bolt a new one on, or remove the battery cover and place a new battery in the Torque-Link. Another application could be root cause analysis for rotating machinery failures. So this would be an application where the customer may want to use higher frequency analysis in order to look at torsional vibration or driveline resonance. So that would possibly be a burst mode application where you look at the data at up to 4 kilohertz. Or even if you want to do streaming in this application, this would be one where you would use higher frequencies such as 512 Hertz. But then you'd be able to look at, Lord has had a customer that has used many torque links, over 10 torque links for this application on fracking pump trucks where there was a driveline resonance that was causing failures of the drive shaft. Data from the torque links were able to be used to analyze what these frequencies were and help provide a damping solution to remove the problem. Additionally, Lord believes that torque links can be used as a new tool for condition-based maintenance. So currently, lots of industrial facilities use accelerometers and thermocouples to measure bearing vibration, pump vibration, machinery vibration in general, and temperature to diagnose failures and help plan maintenance cycles. Measuring torque output from pumps and machines and motors could also be a good way to increase the accuracy and identify other problems which may not be picked up by vibration or temperature early in order to help plan the scheduled maintenance, do planned shutdowns, as opposed to losing a machine during a shift and then in some cases losing potentially $1 million an hour due to machine downtime. A final application could be feedback for drive or fly-by-wire systems. With a current battery-operated torque-link, that's likely going to be test and development for drive-by-wire or fly-by-wire systems. But in the future, as we go forward, some of the updates that we're planning to the torque-link, including the inductive power, could make it feasible for a always-on production-type feedback system for drive-by-wire or fly-by-wire applications. So some key takeaways. The torque-link is an easy-to-install wireless torque measurement system. Fits any shaft diameter from 2 to 6 inches. And as I said previously, we can do custom sizes. Just need to call engineering to discuss for a custom quote. This device can be single or dual channel because the electronics are all on one side. So it just requires a strain gauge installation for the parameters the customer is interested in measuring. It is compatible with all other Lord MicroStrain wireless nodes. And it has been tested to DO 160 standards for temperature, vibration, and humidity. If there's an aerospace application where a customer is interested in having a specific vibration spectrum tested, we can perform that test within a couple of days. If there's any questions or need more information, please contact sensingsales@lord.com or call us at the standard sales number. Thank you.